So our goal now is to solve a differential equation. So this is more the new calculus. What does solving a differential equation do? What are its benefits? So again, differential equations are simply equations involving a derivative. That's what the word differential equation means. So it's an equation involving a derivative. And what we are going to do is use integration and known conditions to help us find initial values. So a differential equation typically involves a unique equation. It satisfies some initial condition. Sometimes these are referred to as initial values. The order of a differential equation is the order of the highest derivative involved. You will often, or maybe sometimes hear these referred to as IVP problems for initial value problems. We are striving to solve the differential equation with a goal of getting y by itself. So our goal is to get the y by itself. So it's like back in the day when you used to solve an algebra equation and you got the y alone. Solving differential equations typically involves taking an integral and then plugging in initial values. So typically involves taking an integral and plugging in initial values. So we have solving initial value problems. So it says solve the initial value problem explicitly, aka by separation of variables. So implicit means that your variables cannot be separated. So when we had implicit problems, it meant that the x and the y's were stuck together. In an explicit problem, it means that you can get the y alone. So we have dy dx equals sine x. So what we want to do is get the y's on the left, the x's on the right. So that means we're going to multiply both sides by dx. So I have dy equals the sine of x dx. So again, at this point, this looks like a derivative like we saw in u substitution. You had dy equals da-da-da dx. Well, it also should look like a reverse integral problem to you. So if I were to integrate both sides, or slap that integral on there, this is really just like the constant 1 integrating dy. So if you go backwards, the integral of 1, or a constant dy, is really just y. The antiderivative of sine is its reverse, right? So derivative of sine is cosine. Antiderivative of sine is cosine. But again, because there's no negative there, it becomes negative cosine x plus, we have no bounds, so we need a c. All right. Now, at this point, I have kind of solved my initial value problem. What I have not done is included those initial conditions. So the initial condition was that when y was 0, or y of 0, was equal to 2. So it means when x is 0, y is 2. So we're going to replace all the y's with the 2, the x's with the 0, and solve for c. So you can see how this is a combination of solving indefinite integrals as well as kind of taking it one step further because now you have to isolate your dy's. We're also going to get into more complicated ones. So cosine of 0 is 1. So this becomes 2 equals negative 1 plus c. Adding 1 to the other side, I see that c is equal to 3. So what that means is in a solved initial value problem, we have y equals negative cosine x plus 3. Same idea. Solve the initial value problem explicitly, aka by separating your variables. So I have dx dt equals 1 over t minus 1 over t squared plus 6. So in order to solve this, I have to get the dt's with the t's, the dx's by itself. So I get dx equals 1 over t minus 1 over t squared plus 6 dt. At this point, I'm going to integrate both sides. The antiderivative of dx is x. So again, you want to pay careful attention to what your variables are. Antiderivative of 1 over t is not 0. It's ln. Antiderivative of negative 1 over t squared. What's really like negative 1 to the t to the negative 2. So you add that power back. So you get t to the negative 1, a negative and a negative become a positive 1 over t. Add the t back to my 6. And we can't forget our plus c. We are given that when x is 0, t is 1. We are given that when x is 0, t is 1. So we're going to plug a 0 in for x, a 1 in for t, and solve for c. Natural log of 1 is 0. That leaves 1 plus 6, which is 7. So you have 7 plus c equals 0. So that means that negative 7 equals c. Which means that x equals the natural log of the absolute value of t plus 1 over t plus 6t minus 7. You must have the absolute value around that natural log because it is not the natural log of a number with a restricted domain. So you must have a natural log in order to ensure that nothing you plug into ln for t is negative. So what happens when we have discontinuity in our initial value problem? What happens if we have discontinuity in our initial value problem? So we have dy dx equals 2x minus secant squared x, whose graph passes through the point 0, 2. So what we know about secant is that secant has multiple vertical asymptotes. So our secant graph kind of goes increase, sad face, another concave. So that pattern continues indefinitely with multiple vertical asymptotes. So that affects our initial value problems in the sense that we have to talk about their domains. So when it says to find a particular solution, what happens is these slope fields that we're going to create and talk about tomorrow are going to have these moments where the slopes are undefined. And that will happen every time you have an x value and your slope becomes something over 0. So if you think about this equation, it's dy dx equals 2x minus 1 over the cosine of x squared. That's really what that means, because secant is cosine. So secant squared is really 1 over cosine squared. So you need to ask yourself, okay, when is the cosine equal to 0? And the cosine will be equal to 0 at pi halves. But what happens is this graph is manipulated by 2x. So we want to know when 2x is equal to 1 over cosine of x squared. Which is really like saying, okay, when does 2x cosine squared x equal 1? This one, I can show you. And that ends up being one of our Pythagorean identities. So again, that's our double angle theorem. So we just need to be careful and cautious of, okay, when is that equal to 0? We know that it's going to occur at those pi halves. So we need to restrict this so that it lives beyond or within each of those bounds. So keeping this in mind, we have this on our back burner. We're going to use that as we plug in our points and discuss, okay, does this affect my initial value point? Is 0, 3 going to work? So if I plug in 0, am I going to get out a value that works? Remember that 0, 3 has to go into the original, not our derivative. So right here, this still represents the slope. So we just need to make sure that this is valid at x equals 0. Okay? So what you do is still separate those variables. The important thing, and I've been stressing it, is that every time you integrate, you must have a dx or a dy or a dt written with each integral. They kind of go together. Can't have one without the other. Antiderivative of dy is y. Antiderivative of 2x is 2x squared over 2. And then antiderivative of secant squared is tangent. So again, derivative of tangent secant squared. So we get minus tan plus c and again, doesn't work plugging in a 3. So in this case, we get that our C value is equal to 3. And again, it is fair and valid for us to plug in 0. And we end up getting here 2 times 0 is 0, cosine 0 is 1. 0 minus 1 is -1. Since -1 doesn't equal 0, we are happy because that means that my slope is not undefined. Like we actually have a slope when we plug that in. So we are happy our slope in this case is -1. Therefore, my C value, initial value, all of that works. So again, if the slope at your point is good, and we are also happy. So the slope is -1, my C value is 0, so my equation of my line is x squared minus tan x plus 3. We can also solve initial value problems using fundamental theorem of calculus. So if you go back and you think about our fundamental theorem of calculus, fundamental theorem of calc said that if you had an integral from a to b of f prime x dx, that was equal to f of b minus f of a. So again, that's our fundamental theorem of calc. So in the case of this problem, that initial condition is x of 0 equals -3. So it's like saying that a is 0 and f of 0 is -3. So it's really like a plus c. So we're looking for f of b in a way. So again, that is kind of like the reverse of this formula, where we have like our input to an output, etc. All right. So again, isolating, getting that initial value problem by itself, you get du equals blah, 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 dx. Now, the idea is that if you are anti-deriving that, then we end up getting this u equals blah, blah, blah plus c. That plus c is my fundamental theorem of calc idea. So we're going to add bounds on here, such that we are bounding this from that 0. Like I said, a was 0. B in this case is x. My f of a was -3. So really, this is kind of like f of not u anymore, but f of x to match my upper bound. But remember, f of x is really the same as u, because u is the function, or the y value. F of x is function notation for a y value. So they're interchangeable. That f of x is interchangeable with u. They mean the same thing. So not f of u, but f of x and u. So again, I repeated, talked about that input-output fundamental theorem of calc idea. So what is the antiderivative of u to the x? with 2 plus cosine x dx, what happens to my output? So again, we can't really anti-derive that. So we just think of it in FTC form. But our final answer is really just this. This is your answer. That's your answer. The bottom is just rewriting it with the A's and B's. So pretty much up to this point, I haven't showed you anything new. I really just showed you what we've been doing with fundamental theorem, what we've been doing with c-values. So that is kind of how you can do it when you separate and you have your exact answers. As we get more and more into this unit in the calc, we're going to see that the equations we look at are more difficult. We have our E's, our LNs, but especially the E's. And we're also going to look at slope fields. So this separation of variable strategy is super important with slope fields, because what we do is we look at each point and we find the slope at each of those particular points. So on AP, there's typically a free response question every year that is a slope field. It has some variation of a problem that looks like this. So it'll say, solve the differential y prime equals 2x over y. So now I have multiple variables. I have y's and x's. We still need to use the strategy we used in the previous 3 examples, where I get the x with the dx, the y with the dy. So remember that y prime is really just another way of saying dy dx. So y prime equals 2x over y is really the same as dy dx equals 2x over y. So our goal is to get the y's with the y's, the x's with the x's. So I'm going to multiply both sides by y, and I'm going to multiply both sides by the x. So get the y's with the dy's, the x's with the dx's. So that gives me y dy equals 2x dx. If I want to solve this differential, that means I want to get rid of the dx's and get rid of the dy's. So we're working backwards. So just like before, I'm going to integrate both sides. But now, because it's not just like a 1 dy, it's a y dy, you have to integrate the y. So integrating y gets 1/2 y squared. Now, both of these are unbounded, but we only put one c. We always put the c's with the x's. So we're only going to do one c, and it's always with the x's. So I have 1/2 y squared equals 2x squared over 2 plus c. We're going to solve for y. So I'm going to multiply everything by 2. Remember, the c just absorbs anything we do to it, so you're not going to write 2c. It just gets absorbed into that c value. So it's just c. And then we want to get y alone, so you have y equals plus or minus the square root of 2x squared plus c. So down at the bottom, you have examples of equations that essentially are just examples of what's the original look like, and then what's it look like if you put the y's on one side and the x's on the other. So for all of our problems, that's what we are going to do. So example number 2. We have dy dx equals 4x cubed cosine y. So once again, what you want to do is get dy's on the left, dx on the right. So we're going to multiply by cosine y, dy equals 4x cubed dx. Once you have all your y's on the left and x's on the right, you take your antiderivative. Antiderivative of cosine is negative sine. Just sine. Equals 4x 4 over 4 plus c. Canceling 4's. Isolate your y's. How do you get rid of sine? You take the inverse. Okay, and then the last part is how do you do that with a particular solution? So again, that's what we started with. It's just the ones we started with had easy y-sides. Now, my y-sides have actual antiderivatives other than just the y. So we're going to flop the x squared plus 4 and the y. We're going to flop the dx over to the other side. So here, how do you move over y? You divide by y. So that means I have 1 over y dy equals x over x squared plus 4 dx. Integrate both sides. The antiderivative of 1 over y is ln. The antiderivative of 1 over y is ln because that is our rule. The antiderivative of that x squared plus 4 with an x on top is going to be what type of problem? It's a use sign. Because down here, I have x squared plus 4. Up top, I get 2x dx. Divide everything by 2. I get x dx. And u over x squared plus 4. So I have 1/2 the integral of 1 over u du. So this also becomes an ln. How do you get rid of an ln? Either sides. Remember that the rule is really like this is e to the 1/2 times e to the ln of u. It's like a power to a power. So that 1/2 doesn't affect that ln of u. Like they're still going to cancel each other, because that's really like a power to a power when you have two things multiplied as an exponent. So that ln of u is really like a power to a power. And then the plus c is really like e to the c, which we know is just a constant. Because anything added inside an exponent is really multiplication. So you get y equals u to the 1/2 times e to the c. Remember, c sort of absorbs everything. So we can just think of this whole thing as c. So it's like c square root of u, which is x squared. And then you can solve for c. And sometimes, honestly, like this is kind of gross and messy, right? Like, and plugging in here is going to be gross and messy. You can actually solve for c at any point in time. So I could have solved for c like way back up here, where I had y, which is 2, equal to e to the 1/2 ln x squared, which is -3, which is 9, plus 4, plus c. So you could have solved for c way back there. You could have solved for c here. It really doesn't matter where you solve. So you have 2 equals ln of 9 plus 4 is 13. So the e's and the ln's, like I said, cancel each other. That's really like being multiplied. So you have 13 halves plus c. Subtract that over. 13 minus 4. And that's what we're doing right here. And again, if you plugged in 2 and then worked backwards and solved, we would see that as well. Now again, you'd end up getting that plus or minus, and you would have to know that it's the negative because this is a negative square root. Take a minute, let that absorb, and then I'll get